Every time you scroll through a feed or stream a video, you are relying on technology born from 1960s Cold War nuclear era. In 1960s, the US military realized their communication infrastructure had severe structural weakness. It relied almost entirely on traditional telephone lines, which required a dedicated continuous circuit to stay open between two callers. As this diagram illustrates, traditional networks operated on a hub and spoke model. In nuclear standoff, this was a liability. A single strike at one of these central hubs would instantly sever communication for an entire region. At the same time, the academic world faced a different bottleneck. Computers in this era were exceptionally rare. Their cost were around millions of dollars and took entire room and were entirely isolated from one another. If researchers at Stanford needed to use specialized machine in Utah, they couldn't log in. They had to physically travel there or mail magnetic tapes across the country. The Department of Defense's Advanced Research Projects Agency, which is ARPA, stepped in to solve both military's fragility and universities' isolation with a single unified project. To ensure communication could survive a nuclear strike and allow researchers to share resources, engineers had to invent a communication architecture with no single point of failure. This solution was a concept of packet switching. Instead of holding open a fragile continuous phone line for an entire transmission, they changed how the data moved through wires. Packet switching takes a message and it chops into tiny independent pieces. Each packet is dispatched into web of connections, finding its own unique route through the network. If one pathway is destroyed, the packets could take another route which is not damaged. Once they reach the destination, they use built-in instructions to reassemble the original message. To make this routing physically possible, engineers at firm BBN built specialized gateway called interface message processors or IAMPs. Looking at this early network sketch, we can see the nodes for the first real-world test. On October 29, 1969, an IAMP at UCLA established a connection with a machine at the Stanford Research Institute. A programmer at UCLA tried to type a simple remote command, the word login. He typed L and the Stanford computer received it. He typed O, but the system crashed this time. Because of the crash, the first word of this internet was simply LO. Despite the anticlimactic start, the test proved that decentralized machine to machine communication was possible. Once that connection was proven, ARPANET scaled across the country. Developers realized they could build entirely new applications on top of routing infrastructure. In 1971, Ray Tomlinson wrote an application that allowed users to send personal messages to one another. To tell the network where to route these nodes, he chose a rarely used character. There is the @ symbol. The mid 1970s, the system hit a wall. The military tried to add ratio and satellite systems, but these networks used different software codes they couldn't understand. Researchers Vint Cerf and Bob Kahn solved this fragmentation, developing a centralized language, which is the Transmission Control Protocol, and the Internet Protocol, which is TCP/IP. TCP/IP functions as a universal digital translator. It sits as a layer between over internet, forcing incompatibilities of computers to format their packets the same way so users could interact. To make navigating these connections manageable for people, the domain name system was introduced in 1983. It converted complex IP addresses into names like .com or .org. Tracing this timeline, we can say how these standards drove the growth. The switch to TCP IP in 1983 allowed ARPANET to interlock with government, academic, and networks worldwide. By 1990, ARPANET was formally decommissioned, that is, it was closed, entirely stopped because there were many inventions like this which led to this modern internet. This project was designed to survive the nuclear apocalypse by eliminating the central control. In doing so, it demonstrated that the centralized architecture provided the resilience needed to connect the global digital world. So due to all these cold wars which happened in past, it led to the innovation of all of these transmission packets or packet switching concepts which we have these days. And the main question which they questioned themselves was, what if we built a network that had no single point of failure, a network where data could find its own path even if parts of it were destroyed, because one nuclear strike otherwise may have destroyed like the entire network, because whatever information which people may need to send those days were via a phone call. So ARPANET introduced something called packet switching, which instead of having one continuous stream, your data gets broken into small chunks, and those chunks are called packets. Each packet finds its own way route across the network, and they may take completely different paths depending on which one is a better path, or if a path is destroyed, they just take another route. So whatever started as a Cold War defense project became a foundation for entire modern internet, email, streaming, social media, every other thing is built on top of it. So that's the ARPANET era. If you found this video interesting, make sure you like and subscribe, and I'll see you in the next one.